Okay, good morning, everyone. For today, we'll continue and hopefully finish module 3 so that you can get going with homework 4. Let's talk about homework 4 and probably the adjustments that we will do kasi mukhang may mga pinagkaabalahan kayo with your other class. So let's make the adjustments later. Let's try first to finish our discussion about the salient points of module 3. So I guess last time we stopped with proposition 18. Proposition 18 is simply asserting that the set of all linear transformations, which we call Hom of VW, is a vector space under usual function addition and scalar multiplication. And again, the proof took advantage of Theorem 3, or the Compact Criterion, in which we noted that the set of all linear transformations is a non-empty subset of the set of all functions from V to W. So kasi pag yung isang subset, ang pinakamadaling paraan paano ipakita na vector space, yung isang subset ng isang vector, ipakita ng isang set ay isang vector space, is to see if you can find a vector space na superset ng given set. And then if the usual operations are attached to the subset, then you can use Theorem 3 and just show closure under addition and multiplication. And that is sufficient to prove that that subset is indeed a subspace of the vector space. And so it is a vector space on its own right. And that's what we did with proposition 18. We didn't go through all 6 or 7 conditions for it to become a vector space, but rather just look at the closure under addition and multiplication. By the way, I think some of you medyo na interchange yung preposition o yung position in terms. When you say closure, it is the set is closed under the operation. So ang dinidescribe ng closure ay yung set under the operation, all right? So siguro kaya mayroong iba na 4.99 dun sa previous homework. So I just need to take care of those tiny details. So if you want to revisit the proof, it's in here. Okay. All right, so okay. Remember last time when we talked about basis, I said in the module repetitively that finding a basis is worthwhile because the basis contains, or a basis contains all the information that we need to study the linearity or the linear properties of the vector space. And linear transformations actually is one of those things that we can study by just looking at the basis for our given vector space, and that is given in Theorem 19. So if we will read Theorem 19, it looks a bit technical. So you consider vector spaces V and W over a vector, over a field F, and you consider a basis B for V. If F is a function from B to W, so here remember curly F is the set of all functions with domain B and codomain W. So F is merely a function that assigns to every element of the basis of the basis B an element of W. Then it says here that there exists a unique linear transformation such that L of B is equal to F of B. So essentially, though Theorem 19 is phrased in a very technical fashion, it just tells us that pag meron kang function na nag-a-act doon sa lahat ng elements ng given basis, then that function F builds up a homomorphism or a linear transformation. So kung meron kang function na ang domain ay yung basis, ibig sabihin makakabuo ka ng linear transformation from that. Okay? So every function on the basis induces a linear transformation L. And not just a linear transformation, but that linear transformation is a unique linear transformation. So here we need to prove two things. So basically we start from having a fixed basis B and then a fixed function F that acts on the basis elements. And we want to show number one that we can find a linear transformation such that this property is satisfied, okay? So existence yung unahin natin i-prove. Now, I guess the proof here uses a proof by construction, which is usual thing when you're trying to prove the existence of something. To prove that something exists, show me an example of such thing. So in this case, we are claiming that there exists a linear transformation. So our proof for existence will be on defining what that linear transformation is. And the only thing that is required for that linear transformation is that this statement should be true. All right. And then after we have proven existence, what we'll do is to prove uniqueness. And I guess most of you are now familiar with how to prove uniqueness, or at least the usual way of proving uniqueness. We will assume that there exists two different linear transformations and show that eventually they must be equal to each other. All right. So let's dig into the proof. So let's have, okay. So again, here in the proof, I start with a basis. And remember that if you have a basis, then every element of the vector space can be written uniquely in terms of a linear combination of the basis elements, right? So wala na, when we say uniquely, can uniquely be written, that means up to a choice of scalars or ordering of the scalars. So wala nang ibang linear transformation expansion or basis expansion yung element V, except the one given in 46, right? Now, let's start the construction of the linear transformation. So here, I will define a linear transformation from V to W, and you see here that I define the image of a vector V to be the summation of the coordinates of V times the function value of the B sub i's. All right. So again, I don't know if I mentioned it in the class meetings, but definitely in the modules, I think I defined the alphas in the unique representation to be the coordinates of the element V with respect to the basis B. All right. So yung mga scalars na yan, alpha 1, alpha 2, alpha 3 until alpha n, siya yung coordinates ng vector V with respect to the basis B. Okay. Now, how did we define the linear transformation? Well, for this linear transformation, ang image ni V ay mako-compute ko by first looking at the coordinates of V with respect to the basis B. Titingnan ko yung basis expansion niya given by 46. I'll take note of the scalars. And then what I'll do to get the image of L under the image of V under the transformation L, I'll have the sum of the coordinates times the function value of the B sub i's. Well, remember that we started with a fixed function f, and that function f is a function from the basis to W, right? So ang domain ng little f ay mga basis elements. That's why I compute the image of the basis elements, multiply it by the coordinates of V, the corresponding coordinates of V, and then take the sum of those products. That will give me the image of V under L. Okay? So kung nakikita nyo talaga, this linear transformation is completely determined by the action of F on the basis elements. So basically, what happens on the basis elements drives the linear transformation. Okay? So that's why we said that this linear transformation is induced by the basis elements, or is induced by the action of F on the basis elements. All right. Now, first thing to do whenever you are defining something, you need to make sure that this is well defined. Okay. Now, there are several things to check if your function is well defined, because here we're claiming that this is a linear transformation. So in the first place, L should be a function, right? But is it properly defined for all V? Well, it is properly defined because number one, unique yung coordinates with respect to the basis. So that means the alpha i's would be fixed for any vector V. So isa lang yung makukuha nating set of coordinates for any vector V. And then F is a function. So ibig sabihin, si F ay function from the basis to W. So F of BI is well defined because BI is an element of the basis B. The function value is an element of W. This is a scalar in F times an element of W. So that means this is another element of W by closure under scalar multiplication. And then if you take the sum of elements of W, then that means you get another element of W by closure of the vector space W under addition. So indeed, si L, ang domain niya ay V at ang codomain niya ay W. All right, so it is a map. And if you have a V, it can only be assigned to a single element of W. There's no other possible assignment for V other than the one given in 46.1. So well-defined function CL. Okay, and again, that could be attributed to the fact that the basis expansion of V given in equation 46 is unique. All right. So I hope that convinces you that L is indeed a function. Now the next step is to show that L is a linear transformation, because in the theorem we say that there exists an L, and our candidate or our guess for that function L is this guy. So the next step in the proof is to show that L is a linear map or a linear transformation. So in order to show that this is a linear transformation, first we need to show addition is preserved, right? So I'll take two vectors in V, say V1 and V2, and then I want to show that the image of V1 plus V2 is the image of V1 plus the image of V2, right? Now, I was thinking of a better way how to write this part of the proof, but just bear with me for a little bit here. And then if you have questions, just let me know. Okay. Remember, para makuha yung image ng isang vector, kailangan natin yung basis expansion, right? So I suppose here V1 is written with coordinates alpha with respect to the basis B, and then V2 is expressed with coordinates beta with respect to the basis B. Well, the beta I prime and the bi's are from the basis. Okay. So ang idea dito ay pinaghiwalay ko lang na inaccept ko lang yung possibility that V1 and V2 might be represented by different basis elements. That's why I used a different notation for the basis elements for V2. Though I could have just said na pwede kong gawin yung trick natin from homework 2 na kahit anong vector elements can be written as a linear combination of exactly the same vectors, except that we will allow some of the scalars to be equal to 0. So I could have done that, pero ba't nga ba hindi ko pinili? Probably, I don't know, just my choice at that moment when I wrote this. I chose to write them differently. Okay. Now, so this would be the image for, or this would be the representation for V1 and V2. Now, if remember, I want to show that LV1 is equal to LV1 plus LV2. So I need to look at how does the image of V1 plus V2 looks like under the transformation L. So kailangan ko pala munang hanapin ano yung representation ni V1 plus V2. Well, let's just write it here. So then V1 plus V2 can be written as the sum of the alpha i's, bi, going from 1 to n, plus beta I, bi prime, I from 1 to m. And then I can think of it as, dahil ito ay basis elements din, so I can treat this as a long summations. And so I can think of the coordinates for V1 plus V2 to be alpha 1, alpha 2 until alpha n, comma beta 1, beta 2 until beta m. So it would be a longer set of coordinates with length n plus m. The argument will still work if some of the beta i's and the beta I primes are equal to each other, meaning we use the same basis elements for the representation of V1 plus V2. But what I'm after for here is a not so restrictive way or basis expansion for V1 plus V2. So and then remember, how did we define L? So yung L, kukunin mo lang daw yung coordinates nung argument or nung element ng domain, tas i-multiply mo sa f of the basis element, right? Now, since this is our basis expansion for V1 plus V2, or one way to write the basis expansion for V1 plus V2, then the image of V1 plus V2 under the linear transformation L would be the summation of the coordinates times the function value of the corresponding basis element. So, ibig sabihin, alpha I, yung mga alpha i's, part sila ng coordinates. So, i-multiply ko lang sila ng function value ng corresponding basis elements nila. So, that came from here. I copied a scalar, evaluated f with the bi's, and I got this. And then for the betas, did the same thing. So, I put beta I there, and then I took the function value of bi prime, and then there you go. Okay, but obviously that's the nice thing about expanding V1 plus V2 like this, because it comes natural. I don't need to do any splitting. But this one, the first term, is exactly L of V1, because these are the coordinates of V1 times the function value of the basis elements for V1. And then similarly, these are the coordinates for V2, and then this is the function value of the basis elements we used for expanding V2, and so this is L of V2. All right, and so that tells us that LV1 plus V2 is LV1 plus V2. Hence, addition is preserved under the map L. All right. Is that clear? Hopefully that's clear, though tinry ko siyang isulat in just a couple of lines here. But that's basically the idea. Take the basis expansion for V1 plus V2 and then show that you can get LV1 plus LV2. All right? Okay. Now let's try to the let's go to the second part. Now we'll show that scalar multiplication is preserved. And so for that, we need to look at L of alpha V. And the goal is to show that that is equal to this guy. Okay? Now, I guess in my proof, I used 46. Okay. 46 is the expansion for V. So I'm using this guy. So, I mean, okay. L of alpha V, I replaced V by its basis expansion. So I got L of alpha times V, all right? And then I used the distributive property of scalar multiplication over vector addition. So this alpha can go inside that summation, all right? And then I can treat this to be, I can treat this as a basis expansion for a vector element whose coordinates would be alpha alpha I. Remember, that's a scalar times the basis element. So if I want to find what is the image of this vector under the transformation L, I'll just need to copy over the coordinates. So that's why I got the alpha alpha I below, and then I multiplied this by the function value of the basis element. Okay, so we got f of bi, and now take the summation. So here we get the image, which is an element of doubling. And then remember, my end goal is to show that that is equal to that, right? So what I'll do is to take away the alpha from the summation, again by the distributive property of scalar multiplication over vector addition. So this will go out of the sum, and we get this times this guy. But look at this one, right? The alpha i's are the coordinates of V. Bi's are the vectors or the basis elements that we used in expressing V by 46. And so by definition of L, this summation here is just L of B. And then you got this extra alpha outside, so we'll have alpha LV is equal to L of alpha V, which proves that indeed L is a linear transformation. Okay, and so we're almost done. The last thing to show, or actually there are just two things left to show. Number one is that the linear map L satisfy the given property that we claim in the theorem. What's that? What is that property? We say that L should be a linear transformation that satisfies this. L of a basis element is the function value of the basis element. So you can think of L to be the extension of the little function f. And it just so happened that for any function f, then L will be a linear transformation. Okay. Let's see. All right. So let's show that first. So let's show that L of B is equal to f of B. All right. And this is quite easy because L of B, to get L of B in our definition for L, we just need to look at the basis expansion for B, right? But B is a basis element. So by default, supposedly, ito siya. Okay. I going from 1 to n. But B is a basis element. So we know that B is one of the B sabais, all right? So in order to get the basis expansion, pwede kong gawin, si B ay equals sa 1 times yung sarili niya, which is a basis element, plus 0 na lahat dun sa ibang basis element. So you can think of its coordinates to be just a single one, and then the rest are all zeros, all right? So the expansion for B, in terms of the basis, would be 1 times B. And then remember, in order to get the linear transformation, the way we define capital L is copy the scalar coordinate, copy 1, and then take the function value of the basis element, and then take the summation, right? Unfortunately, for the other vector, 0 yung coefficient nila. So magkakaroon tayo dito ng 0 times f of b1 plus 0 times f of b2, and so on for the other basis elements. But all these guys are just 0. So you'll have this. So 1 times fb is equal to f of b. So now we have shown that the linear map L that we defined above is really a function that satisfies the conclusion of the theorem. So that proves existence. Na-prove na natin na may nag-exist na L, na linear transformation L, such that L of B is equal to f of B for all basis elements B. And we're done halfway, or we're halfway done. Now, what's left to be done is to show that L is unique, right? So there is no other distinct linear transformation with the same property. So in order to prove that, let's suppose the contrary. Let's suppose that there exists another linear map M such that M of B is equal to F of B. And my goal is to show that M is necessarily equal to L to show uniqueness, right? Now, so let's see. Let's investigate further. Ito lang yung alam natin so far in M. But remember, we want to show equality of M and L. To show that M and L are equal to each other, then that means M of V should be equal to L of V for any V in the vector space, right? So two functions are equal to each other if their actions on all the elements of the domain are equal. So in order to show L is equal to M, dapat mapakita natin na MV equals LV for all V in the vector space. Okay? So in order to do that, I'll investigate how M acts on an arbitrary vector, right? I'll use the vector V we had in equation 46. So suppose M, so I compute M of V. I'll replace V by its basis expansion. Be careful. I cannot just say that this is the sum of alpha I f of b I, because that is how we define L. But we are assuming that M is different from L. So I don't know exactly how M operates on the elements, but all we know is that M is a linear transformation by our assumption. So I'll use that into our advantage. So dahil linear transformation si M, So pwede kong kunin yung image ng bawat term dun sa summation under M, and then ultimately take the sum, right? So this is basically the first property of linear maps. L of V1 plus L of V2 is equal to L of V1 plus L of V2, right? So pag kinukuha mo yung image ng isang summation, pwede mong computein muna yung image ng bawat term dun sa summation, tapos saka mo na lang sila i-add after, right? That's what we did here. Sort of parang pinagbaligtad ko yung order ng summation at ng function evaluation, which is perfectly fine kasi linear map siya. And then once I am here, I can again use the property of linear transformations. Scalars inside a linear map can go out as a coefficient. So that's how the alpha i's came out of M, all right? And then I'll use the distributive property of multiplication. Hindi ko pala yung gagamitin. What I use next is the assumption that M also satisfies the conclusion of the theorem. Remember, we assumed that M is another function such that M of B is equal to F of B for all B in the basis. So dahil yung mga BI's nasa basis, so M of BI must be equal to F of BI. All right? So that's how this replacement came about. And then what is alpha I F of BI? This is exactly how we define L of B. All right? And so ultimately, we have shown that M of B is equal to L of B for all vector in the space. And so L must be equal to M. And then that completes the proof. All right. Is the proof clear? Or there are some things that you want to clarify? All good? Parang extra quiet kayo ngayon. Or dahil hindi pa hint time for the homework? Okay, wala talagang gusto mag-react, so I'll move on.
Thank you, Pa.
Thank you,
So
sir.
let's.
Thank you.
Okay, yeah. Okay, so let's proceed to example 39. Yun yung mahirap, no, sa linear class, sa online class. Hindi ko alam kung kailan ako mag-move on. Lalo na kahit na last semester I'd been teaching calculus online. Tapos ang hirap minsan kasi hindi mo alam kung mag-move on ka na to the next example kasi yung mga bata hindi sila nagre-react. May mga pabibo pero siguro 4 or 5 students out of 40. Pero yung iba talaga quiet, tapos camera off. So hindi ko alam kung anong ginagawa nila. But anyway, so let's look at some examples. I think these are further examples of linear maps. Oh, but again, essentially, before I leave the theorem, I want to emphasize that yung power ng theorem na to. So, kung gusto mong mag-define ng linear transformation, all you need to do is to assign function values to the basis elements. So kung alam mo lang ay basis, tapos may gusto mong bumuo ng linear transformation. So ang kailangan nilang gawin, mag-assign ng function value dun sa mga basis elements. Pag meron ka ng function values dun sa mga basis elements, then that itself defines the linear transformation. So kung gusto mong computein yung image ng isang arbitrary vector in the space, gagamitin mo lang yung linearity property ni L, kunin mo yung basis expansion ni B, tapos yung basis expansion ni V, tapos makikita mo na kailangan mo lang computein ay yung coordinates times the function value ng basis elements. And then the nice thing about this theorem, it doesn't give any condition on little f, as long as it is a function. So you can put crazy functions as your f. So You can say, oh, f is the cosine function, f is the sine function, f is logarithm, f is whatever you like. F could be as crazy a function as you like. But in the end, as long as it is a function on the basis, on a basis, then that will induce a linear map. That gives me a nice bonus problem in the homework. So, ewan ko kung gusto niyo ng bonus bonus problems. Kasi dagdag trabaho pa rin yun. Pero yeah, maybe I can, aside from probably reducing the number of problems, maybe I can give some extra problems that are not that hard para kung depressed pa rin kayo about homework 1 and homework 2, just to give you a consolation para meron kayong panghatak later. So just remind me about that later in case I forget. Okay. Okay. Now let's look at, oh yes, Jeng.
So sinabi mo kahit anong function, so you can have x raised to n, you know?
Yep, kahit ano.
Okay.
And then yun yung power ng theorem 19 kasi kahit anong function, kahit hindi siya linear, kahit napaka-crazy nung function na may isip mo, basta i-define mo siya dun sa basis, makukuha mo pa rin pag in-extend mo yung function na yon to become para ang domain niya na ay vector space V, ang makukuha mo pa rin ay linear transformation. Okay. Okay, example 39. So in example 39, this is an example of a linear transformation na ginagamit na natin since elementary algebra. So this is called the Polynomial Evaluation Map. I call it EV, which is a map from the set of all polynomials in the indeterminate x to the field f. So if you have a polynomial p expressed in this way, then the evaluation map of p is just the sum of the alpha I c sub I going from 0 to n. So basically what we do in evaluation maps, we just replace the indeterminate x to the I and replace it by c to the I. Okay, because remember, I don't know if you are familiar with the actual algebraic interpretation of a polynomial. Kasi in high school, we treat polynomials as functions, right? So p of x is just a placeholder here. But in algebra, polynomials are actually objects on their own. They are not. They could be seen not as functions, but as algebraic objects themselves. So if you look at p of x, this is basically a polynomial in the indeterminate x. It doesn't need to have a domain. It doesn't have to have a range because polynomials are objects, are algebraic objects. They are not functions. Or actually, probably that's how they began. But now there is no distinction between a function and a polynomial. We are thinking of polynomials as just functions, right? Pero you can think of polynomials as objects on their own. So you can think of, say, 1 plus x squared. Isa siyang algebraic object. X doesn't stand for anything. So it's an indeterminate. So it doesn't stand for any number. So ito ay object talaga on its own. Now, the notion that polynomials can be treated as functions probably is explained by the evaluation map. Kasi ang nangyayari dito, yung indeterminate na x, yung object x, abstract object x, that doesn't stand for any variable, for any real number, for any complex number, they can be replaced by elements from your scalars. And that evaluation works in a linear fashion. So linear mapping, itong evaluation map. So nangyayari, so yung pwede kang mag-assign ng scalars from your field say C0 halimbawa 1, C1 ay equal to 0, C2 is equal to 3, for instance, if I'm working with f equals the set of real numbers, right? And then my evaluation, my polynomial p of x, halimbawa siya ay 1 plus x squared plus x. Pwede ko itong gawin as 1 plus 3 plus 0, where I replace, probably I should put it as a pen remark here, not a laser point. But anyway, so halimbawa, consider the polynomial p of x equals, say, 3x squared plus 4x plus 2. So ang f natin ay r. Okay? And then kukuha ko ng scalars. A triple of scalars. So halimbawa, kukunin kong C0 ay C1, C1 ay equal kay 4, and then C2 ay equal kay, say, equal to kay 3. Kulang pa ba ako? 0, 1, 2. So okay na to. And then that means if I evaluate the polynomial p with respect to these scalars, the scalars should be fixed way ahead of time, right? So given na talaga yung scalars for the evaluation map, so you can think of this evaluation map to be tailor-fitted to 1, 4, 3, to this set of scalars here. So if I do that, I will replace all x to the power 0 by 1. So remember, I can look at the constant to be multiplied by x to the 0. So that means I will replace x to the 0 by 1. Okay. And then x to the first power will be replaced by c1. So this would be 4 times 4 plus x squared will be replaced by c2. So we'll have 3 times 3. So this would be 9 plus 16 plus 2. So that's going to be 27. So the value of the polynomial with respect to the triple 1, 4, 3 under the evaluation map is equal to 27. Okay? Ito yung pinaka-generic na evaluation map. The replacement for the powers of the indeterminate are determined ahead of time. So medyo parang weird because kakaiba siya dun sa usual polynomial evaluation that we know. But that polynomial evaluation is actually a special case. And I guess I wrote that here. So in particular, if you will fix the number or the scalar that you want to put inside your polynomial in the usual fashion that we do as if we are dealing with functions, then we can take c sub I to be c to the power I for every I, for every natural number I, or I equals 0. And then pwede ko nang i-fix yung evaluation map not with respect to an n tuple of scalars or n plus 1 tuple of scalars, but to the single scalar c. So may typo uli dyan. Please correct, dapat evaluation map sub c. C stands for the scalar that we are fixing, the scalar that we plan to put inside our polynomial, all right? And then the indeterminate, or the powers of the indeterminate, the x to the power i's, will be replaced by powers of the scalar c. And that's our usual notation. Or the usual notation that we have for that is p of c. So if I'm going to go back to my example before here, pwede kong i-define yung evaluation map with respect z to the number 0. And I will evaluate p at 0. So by notation, or the usual notation we know for the evaluation map with respect to a single scalar, this is just p of 0. And essentially, we replace the powers of the indeterminates by the corresponding power of the polynomials. So we'll have 3 times 0 squared plus 4 times 0 plus 2 plus 2. Hindi maganda yung 0 to the 0 kasi 0 to the 0 in real analysis is undefined, or in basic algebra. So this will just be equal to 2. And that's the usual polynomial evaluation that we know. And it turns out that the polynomial evaluation is a linear transformation. Okay? All right. So moving on to remark 4. Remark 4 is telling us that the pseudo-converse of Theorem 19 is true. So Theorem 19 tells us that any function or any action or any function acting on the basis elements induces a linear transformation. The other way around is clearly true. If you have a linear transformation, then it induces a function little f. So kung mag-start ka naman sa linear transformation L, kunin mo lang yung action ni little l dun sa basis elements, baka kapag-define ka ng function little f. So every linear transformation induces a function on the basis elements, and Theorem 19 tells us the other way around. So therefore, there is a one-to-one correspondence between the set of all linear transformations on the vector space and the set of all functions on one of its bases. All right, so nagba-match sila. So this seemingly easy way of defining linear transformations might lead us to think na napakarami pala ng linear transformations. Kasi basta makaisip ako ng function dun sa basis, then lagi na ako magkakaroon ng linear transformation. And the other way around is true. Lahat ng linear transformation ay nakakapag-induce ng isang function dun sa basis elements. So it is logical or actually intuitive to think na napakarami ng linear transformations on a certain vector space. Pero actually, example 40 will tell us otherwise, na hindi pala napaka-abundant ng set of all linear transformations among the class of functions on the basis elements, or the basis or the set of all functions on the vector space. So for instance, kumuha tayo ng isang maliit na example. So let f be Z3. So si f may tatlong elements. Consider ko yung vector space of quadruples of elements of Z3. So meron akong yung bawat vector ko ay may 4 na elements ng Z3. So ibig sabihin, ilan lahat yung elements ni V? Well, some fundamental principles of counting will tell us we'll have 3 to the 4th elements, right? So there would be 81 elements for the vector space.
Sir, excuse po. Pwede pong ulit po, sir, kung bakit naging F4, F raised to 4?
Wala lang. Inassume ko lang. Gusto ko lang na gawing example ay vector space. So you can also do the analysis if you say ang vector space ko lang ay si F halimbawa, or ang vector space ko lang ay si F squared, consisting of 2 vectors. Just this illustration, I copied Golan's example. Consider niya F to the 4, which is a random choice. So you can do the same analysis for other vector spaces, right? Because anyway, F to the power n, lagi na vector space. Diba? Na-prove na natin before na F to the n is a vector space. So here, specific vector space, kunwari lang F to the 4, okay? So si F to the 4, merong 81 elements. So kung meron siyang 81 elements, pag kinuha ko lahat ng posibleng functions, kung bibilangin ko ilan lahat ang posibleng functions na pwede kong ma-define with domain V and codomain V. So kung meron siyang 81 elements, kung magde-define ako ng functions, ibig sabihin, sa bawat isang element ni F4, ni F to the 4, merong ilang options. Meron akong 81 choices, right? So if V is in capital V, that means I have 81 choices for f of V. All right? And that happens for all element of V. So bawat isang vector, meron akong 81 choices para maging function value niya. Pero meron akong 81 elements ni V. So therefore, in all, I will have 81 to the power 81 possible functions, right? Fundamental principle of counting. So meron akong 81 raised to 81 na posibleng functions na ma-define with domain V and codomain V. So yun yung total number. Pero ilan kaya sa kanila yung linear transformations? Theorem 19 might lead us to say, dapat malaking portion ng 81 to the 81 kasi napakadaling mag-define ng linear transformation. Kailangan ko lang na isang function na nag-a-act dun sa basis elements, pero meron ng 81 to the 81 na posibleng pagkunan ng action on the basis elements. So probably I will have a lot of linear transformations, right? However, kung titingnan natin, ano yung dimension ni F? Do you guys remember what is the dimension ni V? Ano yung dimension ni V? Kunwari, wala yung rest ng notes. Ano yung dimension ni V? Do you guys remember? If I have a F to the N, ano yung dimension niya?
N.
Exactly. So, ibig
Possible
sabihin,
number of cases.
right. So, ibig sabihin, yun yung cardinality ng basis. So, ibig sabihin, si V, ang dimension niya ay 4. Kasi ano nga yung dimension? Ang dimension cardinality ng basis. Ano yung basis? Can you give me a basis for F4? Well, you can go with a canonical basis, right? So, meron kang 1, 0, 0, 0, 0, 1, 0, 0, 0010 at saka 0001. Apat na elements yan. This is the elementary basis. 4F to the 4. Okay. So meron tayong apat na elements. Then remember Theorem 19 and its pseudo-converse and Remark 5 tells us na sa bawat function, mula sa bawat function, dun sa basis, nakakagawa tayo ng linear transformation and vice versa. So kung ilan yung functions on the basis, ganun din karami yung possible linear transformation dun sa buong vector space. Pero ilan yung posibleng function dun sa basis? Gaano karami yung elements nito? So ibig sabihin, ilan yung elements ni basis? 4, diba? So for every B in V, ilan yung choices natin for F of B?
Four.
Not 4.
Hindi man guro 4.
Tingnan niyo yung codomain. Ano yung codomain? Kasi remember, ang sabi ng Theorem 19, functions from the basis to another vector space, W. In this case, V is equal to W. So ibig sabihin, sa bawat basis element, nag-assign ako ng element ng vector space V. So kung meron akong vector, basis element B, imamap ko siya sa isang F of B, which will come from the codomain, which is V. So ilan yung posibleng choices para sa F of B? Not 4, but
16.
nope. More hula.
81.
81. Right, that's correct. That's 81. Kasi nanggagaling yung F of B sa vector space V. We said that the vector space V has 81 elements. So that means there would be 81 choices for F of B. But how many basis elements are we assigning? We're assigning 4. So first slot, 81 choices. Second slot, 81 choices. Third slot, 81 choices. Fourth slot, 81 choices. Multiplication property of counting tells us that there would be a total of 81 to the power 4, right? And then remark 5 completes the picture. It says that there is a one-to-one correspondence between the set of all linear transformations from V to V and the set of all functions from B to V. So ibig sabihin, F of BV has 81 to the 4th elements. So therefore, HUM VV, the set of all linear maps from V to V also has 81 to the fourth elements. 81 to the fourth is a huge number, right? However, compared to the set of all functions, which is 81 to the 81, 81 to the fourth is very minute. So if you take the percentage, so meron ka lang 0.11 times 10 to the negative 146%, not percent, yun yung fraction ng set of all functions that are linear transformations. So out of the 81 to the 81 possible functions, there are only 81 to the fourth linear transformations. So yeah, it would be 81 to the minus 75%. So napaka-kauntian nila. But you see here, kokonti sila kasi napakaliit ng dimension ni V compared to its cardinality. Okay? So because the dimension of V is just 4, which is little compared to the number of vectors in V. 81 yung vector. So napakadami ng posibleng functions, pero kakaunti yung linear transformations because all linear transformations are defined by the action by its action on the basis element. So yeah, ang liit yung dimension. Kaya siguro pinili ni Golan na example ay 4. Because if you take, say, f equals 3, so medyo hindi ganun ka dramatic yung effect kasi you will just have 3 to the 3 elements of V, so that's a total of 27. Dimension is 3, so you will have 3 cubed over 3 to the 27. Yeah, 3, 3. So pag ang f ay equal kay 3 ay lahat ng transformations magiging lahat ng functions magiging linear transformations, right? So yeah. So pinakamagandang example yung f to the 4. Yung f to the 5 medyo OA na kasi napakadami na niya ng maging elements. 3 to the 5th na. So 3 to the 5th raised to the 3 to the 5th number of functions. Pero ang basis niya lang ay 5, so meron kang 3 to the 5th. Masyado nang maliit para i-compute yung relative quotient na to. Okay? Now, that example teaches us na hindi pala necessarily napakarami ng linear maps. So it kind of depends on the dimension of your vector space in relation to the number of elements the vector space has. All right? Now, let's move on to proposition 20. Proposition 20 is just another way of creating a linear transformation. If you already have two linear transformation, but with different domains. So we have three vector spaces now, V, W, and Y, but they have the same underlying field F kasi nagmamatter yung scalars. So they have the same underlying field. And then we assume that L is a linear map from V to W, and M is a linear map from W to Y. Then the composition, M circle L, is a linear map from V to Y. Okay. So first, I started the proof with a clarification or setting out of convention. We define M circle L of V to be M of L of V. Because in other courses, baka baligtad yung pagkaka-define ng M circle L. So in our class, we define M circle L of V to be M of L of V, right? And I think ito yung sa usual, yung ginagamit natin sa usual algebra, right? So as a basic algebra. Kasi in some courses, probably some that are more focused on algebra, baligtad yung definition nila ng M circle L. This M circle L could be defined as L. This M circle L can be defined to be L circle M. So, pero para clear, ito yung definition natin ng M circle L. So M circle L will be a map from the V papunta kay Y. Okay, so we want to show that M circle L is a linear transformation. So standard naman yung pagpapakita na siya ay linear transformation. You consider two arbitrary elements of your vector space or of your domain. Ang domain ni M circle L ay V. So we'll take two elements of V, add them up, put them inside M circle L. Okay? So M circle L of the sum, well, I'll use the definition of composition. This would be M of L of V1 plus V2. But L was assumed to be a linear map. So LV1 plus V2 is the sum of LV1 and LV2, right? And then this is an element of Y. This is another element of Y. Sorry, this is another element of Y. And Y is a vector space. So that means, wait. Yeah, it's a vector space. Di pala vector space yung kailangan ko. Kasi kailangan ko ma-distribute yung function na M. So what I need to the next line is to use the fact that M is a linear transformation. So this is an element of Y. This is an element of Y. The domain of M is Y. So this is properly defined. M is a linear map. So the image of a sum is the sum of the images. All right. So this would be M of LV1 plus M of LV2, right? But this guy is exactly the definition of M circle L of V1, and similarly for this guy. And so we have shown that the image of V1 plus V2 under the composition is the sum of the images of V1 and V2 under the composition. So addition is preserved. Now, on the other hand, let's try scalar multiplication. So we take a scalar alpha coming from the common underlying field. And probably here you'll see why the underlying field is important to be the same para wala ng complication about the imaging. So here, first line, apply the definition of composition. And then we'll use the fact that L is a linear map. So this alpha will come out of the linear transformation. So you'll have that, okay, times LV1. And you see the importance. Bakit dapat pare-parehas yung underlying field? Because if they will have different underlying fields, this alpha comes from the underlying field for V. But L of V1 is an element of the vector space W. So kung si W, iba yung underlying field, then alpha times an element of W might not be defined. Okay? Kung magkaiba yung underlying field. That's why we need to make sure na pare-parehas yung underlying field, because otherwise, you need to transform alpha to a scalar that belongs to the underlying field of W. Dadami yung kailangan nating mappings para lang ma-discuss itong mga bagay-bagay na to. That's why I agreed with Golan. We'll stick with the same underlying field for all the vector spaces. But if you'll go into more into a deeper algebra, then you can have different underlying fields, but there should be a map that will take this alpha into a scalar that that is compatible with a vector in W. Okay, but thankfully we don't have that problem, so that's the same alpha as the one inside L. And then I'll again use the fact that M is a linear transformation. So that means this scalar can come out of the transformation, leaving us with alpha times M of LV1. But MLV1 is the definition of the composition. Then we'll have alpha carried over as a coefficient. And so therefore we have shown that the image of a scalar multiple is the scalar multiple of the image. Scalar multiplication is preserved, and so the composition is also a linear transformation. So that's why probably, I don't know if you will reach this in modern algebra, but you will see that if you have homomorphisms, it forms a group under composition. And so merong interesting algebraic structure yung set of all linear transformations, because you can attach an operation to it, not just a vector addition and a scalar multiplication telling us that the the set of all homomorphisms is a vector space, but it also has a nice algebra thing. It could be taken as a group. So pwede nyo gawin lahat na natutunan nyo sa modern algebra sa set of all linear transformations. Okay. Okay. Now, probably this would be the meat of today's meeting. Talking about the kernel and the probably later the range of a linear map. But let's see some intermediate terms here. So here we define what the inverse image of an element is. So we write L inverse of W to be the set of all elements of the domain whose image under L is equal to W. So ang domain ng L inverse ay yung codomain kanina. So ang L inverse of W, lahat ng elements ng domain na na-assign kay W. Okay. Note that L inverse of W might be empty. Why? Because L inverse, or the domain of L inverse, is the set W. But not all elements of W is an image of a vector in V. So kaya yung L inverse of W pwede siyang maging empty. Kasi posibleng walang naka-assign na vector V dun sa element W of your codomain. Okay? Okay, in particular, we will be interested into the inverse image of the zero vector. And the inverse image of the vector is called the kernel of the linear operator or the linear transformation. And we denote the kernel to be ker of your linear map. So yung kernel ni L, siya lang yung inverse image ng zero vector in W. In other words, you need to solve what are the vectors in V that gives us the zero vector in W after the transformation L. Okay? So lahat lang na na-assign sa zero vector, siya yung laman ng kernel. Okay? So first thing is that the kernel is always non-empty. Why? Because the zero vector is always in the kernel. Tama? So na-prove na natin to last time na ang image ng zero vector, kung meron kang linear transformation L, ang image ni zero vector I equals to zero vector then, right? I remember we proved it last time. So that should be true, okay? So that makes the kernel non-empty for any linear transformation L. Okay. And then I generalize the definition of L inverse further here. L inverse of a set is just the set of all elements in the domain whose image under L is an element of U. So pag kukunin niyo yung inverse image ng isang set, kukunin niyo lahat ng elements ng domain na ang function value under L ay nagbe-belong kay set U. Okay? Okay. Now we have here exercise 15. Try to prove that if U is a subspace of W, then L inverse U is a subspace of V. Do you guys want to try it on your own or gusto nyong together natin siyang sagutan? Though I don't think it is that hard. What do you think? Let's move on to 41 or let's solve 15.
Sir, sige po. Pwede niyo pong pakita.
Okay, sure, yeah.
Sige po.
So, gusto natin pakita ay subspace ni V, si L inverse of U, right? So, let's probably do that here. Okay. So, we want to show that L inverse of U, sorry. Assumption ko pala ay si U ay dapat subspace. Okay. We want to show that if U is a subspace of W, then L inverse of U is a subspace of V. All right. So our assumption, U is a subspace of W. We want to show that L inverse of U is a subspace of V. So let's use compact criterion in order to show this. We want to show that this guy is closed under addition and scalar multiplication, right? For it to qualify as a subspace of V. Now what we'll do is, okay, we'll take two elements of L inverse U. So let V1 and V2 be elements of L inverse of U. Okay. Then let's first write out what does this mean, right? Anong ibig sabihin na si V1 at si V2 ay element ng L inverse U? So elements sila ng L inverse of U because there exist elements of U such that the image of V1 and V2 is equal to those elements of U, right? So that means there exists a U1 and U2 in curly U such that L of V1 is equal to U1 and L of V2 is equal to U2, right? Yun yung ibig sabihin ng pagiging elements nung inverse image ni U. Okay? Yung function value ni V1 and V2 ay na kay capital U. I just call them U1 and U2 at this point, right? And then we want to show closure under vector addition. So I want to show that V1 plus V2 is an element also of L inverse U. So paano ko mapapakita na si V1 plus V2 ay element ng L inverse U? Any ideas? Any thoughts? Habang I'll sip my coffee, medyo malamig na. Any idea? Walang gustong mag-suggest. What should I do next? Sige, +1 sa homework 4. Yun, ang bilis. Yes, Miss I.
Sir, U1 plus U2 should be in U.
U1 plus U2 should be in U, right? That's probably the conclusion of my argument.
Okay.
Right. That's correct. So, patanda na lang po. Yung mga magkaka-plus, sige, para may makausap naman ako dito, no? Sige, magbibigay ako ng points. Then, at the end of the session probably, or before I give you your markups, pwedeng i-submit nyo as a text dun sa markup, homework for markup, kung ilang bonus points yung nakuha nyo. Alright? Para hindi ko na siya i-keep track. So say you got 1 point today as a bonus. So pagka nag-submit na kayo ng lahat ng problems in homework 4, mag-submit kayo ng text dun sa homework 4 markup, telling me how many points you got in the recitation. Okay? So yeah, Miss I is correct. You got 1 point there. So the idea here is to show that the image of V1 plus V2 is U1 plus U2, right? So that's the end goal for this argument. But essentially, we need to show that because yun yung paraan para mapakita ko na si V1 plus V2 ay nasa inverse image of U. So gusto mapakita na yung function value ni V1 plus V2 ay nagbe-belong kay set U. Because that's what it takes to become an element of L inverse U. Dapat yung function value ni V1 plus V2 ay na kay capital U dapat. So for me to find out if that is really an element of U, I need to find what is LV1 plus V2. And I am keeping my fingers crossed na yung LV1 plus V2 ay madaling mapakita to belong to capital U. All right. So in this case, I'm going to use the linearity of L. Part of the assumption is that L is a linear map. So this is LV1 plus LV2. Okay. And then, by assumption, LV1 is equal to U1. And then LV2 is equal to U2. Okay. Then what do we know about U1 plus U2? U1 plus U2 are elements of W at the worst. Pero ano yung assumption natin about U? U is a subspace, right? We assume that U is a subspace of W.
Of W.
So dapat si U ay closed under vector addition. U1 and U2 are elements of U. So therefore, their sum must also belong to capital U. So therefore, V1 plus V2 is an element of L inverse U. Okay? Now, how do I show the other half? Because we're showing that this is a subspace. So, for 1 point, sino gusto mag-prove ng kalahati?
Sir, yun po ba yung sa scalar multiplication?
Yes. Gusto nyo try? For 1 point. If you want to do it verbally, or pwede akong mag-open ng whiteboard if you want. Meron bang volunteer? Oh, sayang yung 1 point. 2 points. Or baka tinatrap nyo lang ako into giving too many bonus points today, ah. Anyone? No takers? Oh, ayaw nyo, ah. So let's do the other half together. So for the other half, we want to show closure under scalar multiplication. So I'll take an arbitrary element of the field of scalars, okay? So alpha is in F. Then we want to show that alpha V1 is the same V1 I used here. Anyway, that is an arbitrary element of L inverse of U. And I want to show that this is true. Okay. And again, for alpha V1 to belong in L inverse of curly U, that means I want to show that the function value of alpha V1 belongs to U, right? So in order to see if that's true, I'll take the function value of alpha V1, okay? And then here I'll use the linearity of L, okay? And then LV1 is just U1 by assumption, right? And this should be in U because U is a subspace. By the way, one notation that people use for subspace is less than or equal to. Hindi ko lang siya in-introduce kasi baka sobrang ng daming notations. But for shorthand, okay, let's use less than or equal to for subspace. So, sorry, not V, but this is subspace of W. So that means U must be closed under scalar multiplication. So this is an element of U. This is a scalar. So alpha U1 must be mu. So therefore, alpha V1 is an L inverse of U. Okay? And that completes the proof that indeed, if U is a subspace, then L inverse of U is also a subspace of V. Okay? So, hindi lang pala vector addition at scalar multiplication ang napreserve ng isang linear transformation. This example also show that being a subspace is somewhat preserved by a linear transformation or the inverse image of a linear transformation. All right, I hope the proof is clear. And with the proofs that we're doing, hopefully, nakakaroon kayo ng idea how to go about proofs, what are the nice proof strategies. Because writing proofs, I think, is something that you cannot really teach. There's no template for writing proofs. Meron kang methods of proof like proof by contradiction, proof by construction, proof by mathematical induction. Pero yung process na gagawin mo inside the proof, I think there's no hard and fast rules. Talagang experience lang yung experience yung best way to learn how to prove. Okay. So let's see. Some examples here. Example 41. So we consider a field F and a linear transformation, L, from F3 to F4. So meron kang 3 vectors, ina-assign natin siya sa isang 4 vector. Okay? Naglalag din ba yung annotation sa inyo? Kasi in my monitor, naglalag din siya. But anyway, okay. All right. So first thing is that here I'm trying to look for L inverse of 1, 1, 1. So if I'm looking for L inverse of 1, 1, 1, I need to find what are the elements of the domain, which is F3. Ano yung mga elements nung domain na ang function value ay 1, 1, 1. So in order to find that, I need to solve this equation. When is L of V1, V2, V3 equal to 1, 1, 1? Yun yung kailangan kong isolve. Okay? Now, in order to solve that, I need to know how L, V1, V2, V3 are computed, are transformed by the transformation L. So the function value is equal to this guy. Hindi ko na nakikita yung laser point ko. Pero nakikita nyo ba siya, guys? Or delay din?
Yes po, nakikita sir.
Nakikita naman, sir.
So yung sa laptop ko lang yun. But anyway, yeah. So kailangan ko hanapin ano yung mga elements ng domain na namamap kay 1, 1, 1. So kung meron akong element ni domain, mamamap siya sa 1, 1, 1, kukunin ko yung function value nito. By definition, I'll get this guy. Equate ko lang siya sa 1, 1, 1. And then I'll solve for V1, V2, and V3. But unfortunately, here you see that the second component is always 0. Meanwhile, 1, 1, 1 always has the unity, 1. Pero kasi sa field, ang 1 ay hindi pwedeng mag-equal kay 0. The unity cannot serve as the the unity cannot serve as the additive identity as well. So in any field, 1 is not equal to 0. So that means, imposible na makakuha ko ng element ng domain na namamap kay 1, 1, 1. So that's why the inverse image of 1, 1, 1 is empty. Okay. So another implication of this is that you can say that 1, 1, 1, 1 is not in the range of the linear transformation. Although I haven't defined what the range is, pero pwedeng ganun yung isipin nyo. Walang element ng domain na namamap kay 1, 1, 1, 1. Okay? That's why the inverse image is empty. While on the other hand, if I want to look for the inverse image of 1, 0, 0, 0, kailangan ko lang i-equate si 1, 0, 0, 0 dun sa function value ni V1, V2, and V3. And then solve for V1, V2, and V3. If you'll do that, you'll see that V3 must be equal to 0, and V1 minus V2 must be equal to 1. Okay? And so the inverse image of 1, 0, 0, 0, 0 is any element of F3 such that V1 minus V2 is equal to 1, and then the third component is 0. Okay? So there could be a lot of functions or a lot of elements of the domain that has the inverse, that has the image 1, 0, 0, 0. As long as V1 minus V2 is equal to 1, the third component is 0, we'll always get this as the image. All right? Now, I went on here saying that if F is a field of characteristic 2, pag characteristic 2, ibig sabihin ang x plus x ay laging equal kay 0, then magiging subspace daw siya because 1, 0, 0, 0 on itself is a subspace of F4. And then by the previous theorem, we say that if you have a subspace, its inverse image is always a Okay, sorry, may chinek lang ako. Pero yeah, the inverse image is always a subspace. Okay? Though, hold on. Parang may mali dito. Napaisip ako bigla. 1, 0, 0, 0 is a subspace of F4. Hindi siya pwedeng maging subspace of F4.
Hindi yan F2. Pero okay lang kasi is a field of characteristic 2 naman. Pala, no?
Yeah.
Okay. Yeah.
Pero wala yung zero vector. Mukhang mali itong remark ko na to. Kasi wala yung zero vector dito. Ang zero vector ay 0, 0, 0, 0. So para magka-subspace ka, dapat kasama lagi si zero vector. Ang zero vector sa F4 ay 0, 0, 0, 0, 0. 1 cannot be equal to 0. So, yeah. I guess... yeah, I'll double check this, but I guess this is false. So, yeah, sorry about that. Kasi, I hope you see the point. Yung 1, 0, 0, 0, hindi siya subspace kasi wala sa kanya yung additive identity. Wala sa kanya yung zero vector ni F4. So, yeah. Pero field of characteristic 2. So, kung field of characteristic 2, kahit na kasi sa field of characteristic 2, ang zero vector mo ay 0, ang unity mo ay 1, dapat magkaiba pa rin sila. Alright. So, yeah, I think that paragraph is false. So, kindly scrap that.
Pero sir, if V1 minus V2 is equal to 2 yan, sir, pwede yan siya, di ba? Kasi characteristic 2.
Kung ang V1 minus V2 ay equal kay 2, problema ko ay walang meaning yung 2 sa F. Kasi arbitrary field si F. Unless you're saying that F is equal to C. Then
kung
V1,
real number siya, so magiging true siya. Pero kung hindi, so hindi rin.
yeah. Saka ang real numbers, hindi siya characteristic 2. So, yeah. Yeah, so I think there's no way to salvage this example. So let's just scrap that. Oh, that remark. Okay. The important thing here is the next exercise, or this one. Find the kernel of L, because in the homework, you will be asked to compute the kernel for certain linear maps. So to find the kernel of L, remember, yung kernel, siya yung lahat ng vectors sa domain na namamap sa zero vector. So we will be looking for all V1, V2, V3, okay, such that the image of that vector, or that triple of vectors, is equal to 0, 0, 0, 0. Equate ko lang siya dun sa zero vector ni F4, right? So ano yung elements ni F3 na namamap sa zero element ni F4? So I'll solve this equation. So I'll have V1 minus V2 is equal to 0. 0 equals 0, that's fine. V3 equals 0. So we have this system of equations. We have 3 unknowns. We only have 2 equations, so we expect infinitely many solutions, right? Or actually, not infinitely many. It depends on the size of the field, but we expect multiple solutions, right? So the first equation implies V1 must be equal to V2, okay? And then the third component must be equal to 0. So that means the kernel of this linear transformation is just vectors of the form V1, V1, 0. So as long as the first 2 components are equal, the third component is 0, we are guaranteed that that will be an element of the kernel. Okay? Clear ba at least yung idea how to compute for the kernel? Okay? Lagi lang equate nyo yung function value dun sa zero vector. And then see what are the elements of the domain that will satisfy that equation. Okay, exercise 16 is quite nice. It asks us to check if the kernel we computed in equation 50 is a subspace of F3. Again, subspace. So what do we need to check? We need to check. So I'll need to take 2 elements of the kernel. So I'll let A0 and BB0 to be elements of the kernel. Okay? Kasi alam na natin ang itsura ng kernel. 0 yung third component. Sorry. And then parehas yung first 2 components. So that's why I know that this would be elements of the kernel. So there's a tacit assumption here that A and B are coming from the from F or coming from the field F. So, but anyway, these are in the kernel. So we want to show two things. The kernel is closed under addition and under scalar multiplication. So if I add these two guys, AA0 plus BB0, the sum, the addition in F3 is just component-wise addition. So this would be A plus B.
A plus B, A plus B, 0.
Correct. And note that the first two components are equal to each other.
Equal to each other.
The third component is equal to 0. It fits the definition of the kernel of L. So therefore, this is also in the kernel of L. Right? Then let's try scalar multiplication. Alpha of AA0
AA0. So
is equal to alpha A.
Alpha A0.
0. And this is an element of the kernel of L for any alpha in F, right? So kahit na anong scalar in F. Kasi the first two components are equal to each other. The third component is equal to 0. It matches the definition of the kernel in 50. So therefore, the kernel of L, as computed, as we have seen, is a subspace of the domain V, right? Okay. And actually, it's a nice thing to probe whether this will be true for any kernel or for the kernel of any linear transformation. And true enough, hindi pa pala, sorry, spoiler. Pero let's look at example 42 first. This is another example for finding the kernel. So here we define the map L from the set of all 2x2 matrices with real numbers as entries, and the set of all polynomials of degree 2 or less in the indeterminate X. And then we define what is the image of a matrix. So if you put a matrix inside L, then the polynomial that you'll get is this guy. Okay? Now I hope clear na ngayon what's the difference with the codomain and the range in the usual sense of functions. So codomain, siya lang yung set of all candidates for the function values. But you see here, the function values under L are just linear functions. So though yung mga quadratic functions na kay quadratic polynomials na kay P2 rin siya, pero imposible siyang maging image under L. Kasi by definition, ang image lang under L is A plus D plus B plus C times X. Okay? So I say here that it can easily be verified that L is a linear map. So you just need to show that addition and scalar multiplication are preserved in L. So I can probably, let's make it extra credits for the homework if you'd like. So feel free to submit it later. And then, but not required, okay? Just if you want to earn extra points and if you have extra time. And then let's find the kernel of L. Now to find the kernel of L, again, gusto lang nating mahanap ano yung elements ni domain that is mapped to the zero vector in the codomain. So what we'll need to do is to solve the equation function value or image under L of an arbitrary element of the domain. Equate lang natin dun sa zero vector. But again, our codomain is the set of all polynomials of degree 2 or less. So the zero vector there is the zero polynomial. Oops. The zero polynomial is basically 0 plus 0x plus 0x squared. Okay, so that's the zero polynomial. And so we solve. Ano yung definition ng L of matrix ABCD? Here you go. Okay. And then ano yung definition of zero polynomial? Probably I should have written 0x squared also here, but that's perfectly fine. And then two polynomials are equal if and only if their corresponding coefficients are all equal. So the constant here, a plus d, must be equal to the constant here. So that's how we got the first equation. And then we will match the coefficients of x. Coefficient of x here is b plus c. Coefficient of x here is 0. So we must force the issue that b plus c is equal to 0. And then this has nothing to do with x squared. This has 0x squared, which is essentially a non-dependence on the x squared. So this would be the equation that is satisfied by elements of the kernel, right? So we'll just collect. So if you will solve this, you'll see that d must be equal to negative a and z is equal to negative b. All right. So that means there are multiple solutions. So do not try to write it as a single solution. So you can use a parametric definition for the kernel. So the kernel is comprised of matrices such that d is negative a and c is equal to negative b. So all you need to have as parameters are a and b, because c and d are computed depending on a and b. So pwede nyo isulat yung kernel ay mga elements of the form a, b, negative b, negative a. All right. So that's how the kernel looks like for any real numbers a and b. Okay. Now, this would be fun to do. Is this kernel a subspace of M2R? I don't think we have too much time to play with this, so I hope it's okay if I skip that. But you'll just do the same thing to show that this is a subspace, do the compact criterion, right? Show that if I take the sum of two elements of the kernel, I get another element of the kernel, and then take a scalar multiple of an element of the kernel, show that that is also in the kernel, okay? But here's the spoiler. Proposition 21 tells us that the kernel is always a subspace of V, okay? Probably we can do the proofing details here, proposition 21. So it says that if L is a linear map from V to W, then kernel of L is a subspace of V. Okay. So again, less than or equal to means subspace. So kernel of L is a subspace of V. And again, we'll try to do compact criterion here, or use compact criterion. First thing is that I will assume V1 and V2 to be elements of the kernel. And the goal is to show that the sum is also in the kernel. So in order to show that something is in the kernel, that something must have image equal to the zero vector, right? So para mapakita na ang V1 plus V2 ay nasa kernel, kailangan kong computein yung function value ni V1 and V1 plus V2 at ipakita na siya ay equal kay zero vector, right? Para masabi na siya ay naka kay kernel. So, I'll compute L of V1 plus V2. Then I'll use the fact that L is a linear transformation. So I can write it as LV1 plus LV2, right? But what are our assumptions on V1 and V2? V1 and V2 both belong to the kernel. So L of V1 will be the zero vector in W. LV2 is the zero vector in W. 0 plus 0 is the zero vector in W. So this means that the image of V1 plus V2 is the zero vector. So therefore, V1 plus V2 is also in the kernel of L. All right. And then the other part, scalar closure under scalar multiplication. So we let alpha to be in F. Then we want to show that alpha V1 is in the kernel of L. The V1 here is the V1 I used here, which is an arbitrary element of the kernel. So if you want, you can also consider another element V in the kernel if you're bothered with the subscript 1. But make sure that you say that V is in the kernel of L, right? Ginamit ko lang yung V1 kasi na-declare ko na siya sa taas na kernel, na nasa kernel ni L. So, hindi ko na kailangan mag-introduce ng panibagong variable, right? So again, to show that something is in the kernel, I need to show that this is mapped to the zero vector. And I don't think that would be hard. I'll use the linearity of L. So the scalar will come out of L. And then V1 is in the kernel. So the image of V1 under L is the zero vector. Alpha times the zero vector is equal to the zero vector by one of the propositions earlier, right? So that means alpha of alpha V1 is in the kernel. And since the kernel was shown to be closed under vector addition and scalar multiplication, then we can conclude that the kernel is a subspace of V. Okay? So, hindi na pala natin kailangang i-check ito kung siya ay subspace ng kernel kasi we have already proven na kahit anong linear transformation, kunin mo yung kernel ay laging subspace. Okay? I think a more organized proof is included in the module, so you can read it again. All right. So now here we define the range of a linear transformation, or first a range of a subset. If you have Y, a subset of V, then the range of Y is the set of all elements of the codomain that is mapped to the element of Y. So, ang range ng isang subset ng codomain ay lahat lang ng images ng mga elements ni Y. So, range Y ay lahat ng function value ng mga members ni Y. And we will be more interested on the range or the image of the entire vector space. So the range of the entire vector space, or properly, let's call it the range of the linear transformation, is the set of all images of elements of the domain. So ito na yung usual notion natin ng range. So yung range ng linear transformation, siya lang yung set ng lahat ng function values under the linear transformation. Okay? All right, so let's see some examples. So in the following examples, nag-introduce uli ako ng notation dito. From now on, if you have a square matrix, an n by n matrix, let's call it MNF. Dapat to ay MNF, sorry. Another typo there. Okay. So the set of all n by n matrices will be denoted by M sub NF. Okay. Para lang di na lahat natin susulat yung 2 by 2 sa baba kapag ka square matrices. And then here in example 43, we consider a linear map. A mapping from the set of all square matrices with real entries to itself. Okay. Such that function value ng isang matrix ay sarili niya plus yung transpose niya. Okay? If you remember, the transpose of a matrix is just the matrix whose ijth entry is the jith entry. So just recall kung matrix ko ay say ABCD, ang A transpose, pagbabaliktarin ko lang yung coordinate. So yung AA siya ay nasa 1, 1. So baliktarin yung 1, 1. Nasa 1, 1 pa rin siya. So andun pa rin siya. Si P nasa first row, second column. Just interchange the roles of the rows and the columns. So B in A is in the first row, second column. So in A transpose, it's going to be in the second column and first row. Okay. And then C is in the second row, first column. So in the transpose, it's going to be on the first row, second column. And then D in A is in the second row, second column. So in the transpose, it would be still in the second row and second column. So pinagpapalit lang yung row number and column number ng mga elements. Okay? So that's how I got this. So if you have a matrix, a 2 by 2 matrix A, B, C, D, then its image under L is 2A, B plus C, B plus C, 2D. Okay. Again, I don't think it's hard to show that L is a linear transformation. If you want, okay, sure, you can submit it for extra credits, verify that this is a linear transformation. And then the focus here is to find the kernel and the range of L. So here, okay. To find the kernel, again, all we need to do is to get an arbitrary element of the domain, plug that into the transformation, equate it to the zero vector of your codomain. So our codomain is the set of all 2 by 2 matrices with entries over R. So ang zero vector niya ay the zero matrix. Tapos equate mo lang siya sa L of an arbitrary matrix. But the image of an arbitrary matrix was computed earlier to be this guy. So essentially our equation will look like this. All right. So to find the kernel, let's find a condition for A, B, C, and D. Well, coming from this equation, we see that 2A must be equal to 0. That will imply that A is 0. 2D must be equal to 0, so that means D must be equal to 0. And then B plus C must be equal to 0, so that means B must be equal to negative C. Or the other way around. So I can also say, ito yata yung ginamit ko. So it could be C equals negative B. Okay? So these are the conditions on the entries A, B, C, and D for that matrix to belong in the kernel. So you can write it this way. So ang candidate natin para sa kernel ay si A, B, C, D. We found out that A must be equal to 0, so this A must be replaced by 0 when you write the kernel. And then we found out that this D must be equal to 0, so D must be replaced by 0 in the way you write the kernel. And then the condition here is that C is equal to negative B, so you can think of B as a free variable, so put B there. But C must be equal to the negative of B, so that's why I got negative B as the replacement for C there. And you see that the kernel here only depends on one parameter, which is B. And B can be any real number because B is a free variable in our system. Okay, so this is the kernel, and we know from proposition 21 that this is a subspace. You can check, but yeah, that's straightforward as well. Okay, and this is actually finding the range is a little bit trickier. Though alam na natin ano yung itsura ng mga linear transform, ano yung itsura ng mga images. So, kokolektahin ko lang lahat ng posibleng images into a set, and that will serve as my range. So, that's the idea. So, probably one cheap way of writing the range is just saying that, okay, kolektahin ko lang to, lahat ng matrices na ganito yung itsura, and then A, B, C, and D can be any real number, then that's my range. That's fine, though I said that's a cheap way to write the range, but nevertheless, that's an expression for the range. But later, actually, we'll show that we are not really interested in the range, but we are interested in looking at the dimensions of the range. So that's why sometimes we want as simple as possible yung representation natin para dun sa range. Now, here in this bullet, I claimed that the range of L is the set of all symmetric 2 by 2 matrices. When you say symmetric, a matrix is symmetric if the entry on the ijth position is the same on the entry on the jith position. Okay? So yung nasa ith row, jth column ay equal yung sa nasa jth row and ith column. So another representation for symmetric matrices is that it is equal to its transpose. So yun yung ibig sabihin ng symmetric.
Sir, question po.
Yes.
Sir, yung pong, di ba po yung entries natin ay B, tapos may negative B. So, okay lang, sir, na magkaroon ka ng negative B. Symmetric pa rin po siya.
Nasa kernel pa rin siya.
Okay. Okay po.
So, and then, are you asking kung ito po ba ay nasa range? O hindi naman?
Hindi po, sir.
Okay, good. Kasi magkaiba, yung kernel, subset siya or subspace siya nung range. Subspace siya nung domain. Yung kernel, subspace ng domain. Yung range, siya ay, for now, subset nung codomain. Okay? So, though in this example, nagkataon lang na parehas yung range at saka nagkaparehas lang yung range at saka yung codomain at saka yung domain. Pero in general, hindi. Pero for it to be symmetric, dapat equal yung magkabaligtad yung row and column number. Right? They should be exactly the same. Okay, so that's my claim. Ang range ni L ay set of all symmetric matrices. Let's do a quick check. Symmetric ba itong L of A? Well, L of A, yeah, it is symmetric because wala tayong problema sa diagonal entries. Kasi pag binaligtad mo yung row and column number ng nasa diagonal, parehas lang. So, walang nagbabago doon. Equal ba yung nasa 1, 2 at nasa 2, 1? Yes, they are equal. So, it looks like all the results ng pagkuha ng image under L ay symmetric. Okay, so that means ang range ni L ay subset ng set of all symmetric matrices. So I think that is clear, right? Kasi the way L is defined, the result is always symmetric. So the range of L is a subset of the set of all symmetric matrices. So that's what I said here. By just looking at how the transformation is defined, it is clear that the result is always a symmetric matrix. So we can say that the range is a subset of all the symmetric matrices. But it is trickier to show the other way around. Na kahit anong symmetric matrix is an image of a matrix in the domain. So yun yung medyo trickier. How do I show that any symmetric matrix is an image of a matrix in the domain? Okay, in order to do that, I will assume an arbitrary symmetric matrix. So bumuo lang ako ng random na symmetric matrix. And gusto ko makahanap ng element ni domain na pag ipinasok ko dun sa linear transformation L, ang sagot ay itong random symmetric matrix na to. That will show that there is an element of the domain that will give me this random or this arbitrary symmetric matrix, right? So obviously, this is a this is an arbitrary symmetric matrix. And there I'm saying, pwede nating kunin si A to be 1/2 A, B, C, D. Oh, sorry, A, B, B, C. Kasi pag kinuha ko yung L of A, which is A plus A transpose, my A is this guy. So I'm going to have 1/2 A, B, B, C plus 1/2 its transpose. Pag in-add up ko yan, ang makukuha ko ay si matrix B. Tama ba? 1/2 A plus 1/2 A is A. Good.
Yung sa second matrix mo, sir, hindi yan A, B, B, C din.
Ay, yeah, tama. Siguro, yeah, kung ano nang pinagagawa ko dito. So, ito dapat ay A, B, B, C pa rin, no? Yeah, kasi A transpose. The transpose ko lang to. A, C remains on the diagonal, pero parehas lang naman to. So, yeah, thank you. And then 1/2 B plus 1/2 B, that's B. 1/2 C, 1/2 C. So that's going to be C. So take note ko lang to para pag kinorek ko yung final version of module. Okay. All right. So therefore, the set of all any symmetric matrix can be written as the image of a vector in the domain. So therefore, the set of all symmetric matrices is a subset of the range. But we have shown earlier that the reverse inclusion is obvious. So it follows that the range of L is exactly S to R. Okay? And then probably this would be our last example for today, unless you want to continue. Pero I suggest we can stop here. Baka overload na uli. Example 44. So here we consider the set of all C1 functions. Mga C1 functions, siya yung mga functions na siya at yung derivative niya ay continuous. So C1, set of all functions that are continuous and whose first derivative is also continuous. Okay? So sila yung mga C1 function. And I said here, it's easy to show that C1 is a subspace of F. Okay. Now, we will define the linear map or the mapping L from C1 to C1 as the derivative map. In the sense na pag meron kang function galing kay C1, ang makukuha natin ng function ay C1 pa rin. Let me think about this. C1 pa rin ba siya? Maybe just to be safe, I'll put C na lang. Yeah. So dapat siya ay C1 to C. Para wala akong kailangang i-prove na, oh yeah, I think I changed that here already. So yeah, please change that. CL I map from C1 to C, such that pag kumuha ko ng function kay C1, ang function value niya ay yung derivative niya. And that makes this mapping well-defined kasi by assumption, ang derivative ng isang C1 function ay continuous pa rin. Okay? So, formally, L of F is defined to be the derivative of F. Okay? So, yun lang. Kukuha ka ng isang C1 function, ang L of F ay yung derivative niya lang. Okay? Now, let's show that this derivative map is a linear transformation. So first, remember, to show that it is a linear transformation, we want to show that addition and scalar multiplication are preserved. So if I take two elements of C1, I want to show that their sum is also in C1. Okay? And that's easy because pag kinuha mo yung L of F plus G, okay, by using the properties of derivatives, the sum of the derivative of a sum is the sum of the derivatives. So the derivative of F plus G is the derivative of F plus derivative of G. But remember, this guy is L of F plus G. But this guy is L of F plus L of G. Hence, addition is preserved. Okay? And then, eto pala, sinulat ko pala siya in details doon. Ito palang first bullet is I think this is an argument for closure, right? The sum of two functions is also F plus G is in C1. Yeah, this is closure under addition. So that is fine. But the highlight would be this. Ito yung sinabi ko kanina about preserving the sum. L of F plus G is L of F plus L of G, properties of derivatives. The same goes for the preservation of scalar multiplication. If you take the image of alpha F under L, so you're just taking the derivative of alpha F, but any scalar multiplier to a function goes out of the derivative operator. So yung alpha, lalabas siya kasi scalar siya. So alpha times the times the derivative of f. But this guy is exactly the definition of LF. So that's how we got that. Okay. And then, yeah. So that means, indeed, L is a linear map. Okay. Now, the interesting thing is finding the kernel and the range of L. To find the kernel, we want to find which functions are mapped to the zero vector. The zero vector in the space of all continuous functions that is in our codomain. Ano yung zero vector dun sa codomain? Ang codomain natin ay set of all continuous functions. Ang zero vector dun ay yung zero function, right? So in order to get the kernel of L, we need to find what are the functions that are mapped to the zero vector. Or in other words, ano yung mga functions na ang derivative ay si zero vector or si zero function. So if you recall from your elementary calculus, kailan nagsi-zero ang derivative? Nagsi-zero lang ang derivative.
Constant po ang function.
Exactly, that's right. So that means the derivative is zero if and only if f is a constant function. So therefore, ang kernel ay set of all constant functions. So siya yung kernel ng derivative map. And by proposition 21, I think, we said that the kernel is a subspace. So ibig sabihin pala yung set of all constant functions is a subspace of the space of continuous functions. Okay? Okay, and then since this is a subspace, remember pag subspace, vector space din siya, so we can talk about the dimension of the kernel because the kernel is on itself a vector space. So can you think of a basis for the set of all constant functions? Kunwari, hindi nyo pa nabasa yung handout, yung module. So, ano kaya yung ano kaya yung posibleng basis para sa Ker-L? +1 sa makakapag-suggest ng tamang basis for Ker-L. Remember, I'm looking for a basis of the kernel and not the basis of the entire space.
Zero, sir, since ano tawag?
Zero what? Pakidefine. Ano yung f of x equals?
F of c. Constant.
F of c. I want mas particular. Anyone?
F of 0.
F of 0. Ang f of 0 hindi function. Ang f of 0 ay function value lang. So ano kaya yung basis? Can you give me a basis for Ker-L? So remember, ano yung basis? Siya yung subset nung space na linearly independent at nakakapag-span dun sa buong vector space. Ang vector space natin ay yung kernel L. Kasi alam natin yung Ker-L ay subspace ng C1, right? Pero pag sinabi mo siyang subspace, on its own right, it is a vector space. And when you have a vector space, we can talk about the dimension of the vector space. Tapos, ano nga ba yung dimension ng vector space? Ang dimension ng vector space ay yung dami ng elements ng isa niyang basis. So to know the dimension, I need to know a basis for Ker-L, right? Ano yung laman ng Ker-L? Set of all constant functions. So ano kaya yung basis para sa set of all constant functions?
Sir, is it x raised
0, 0.
Come again, ma'am?
X raised to 0 po?
X raised to 0. So ang x raised to 0 ay so you're saying f
Or
of
cx, or
equals
cx raised to 0, sir. Cx raised to 0.
cx raised to 0. Ano yung mga c's?
Where c is, ano po, constant. Or part ng real number. C is in R.
Real number. So yung basis, ano ilalagay ko sa basis? Or gusto nyo bang isulat or didikta nyo na lang?
Dikta na lang, sir, pero I'm not sure. Sir, b is equal to, how do we, sir, how do we write ba?
So, pwedeng, bigyan niyo ako ng isang specific element. Kasi pag sinabi yung cx to the 0, tapos c can be any real number. So, napakadami niya kasi si c kahit anong real number. So, infinitely many. Are you saying that the basis should contain infinitely
Sir,
many?
under interval 0 to 1?
X comes from 0 to 1. Pero si C ay scalar lang naman siya eh. So, pwede siya maging kahit anong real number. Ang usapan lang si X ang nanggagaling sa interval 0 to 1. So, ano yung ilalagay ko? First element ng basis nyo. Specific. Wala nang mga C's. Wala nang mga... Yeah.
B is equal to 1, sir.
1. And when you say 1, you're referring to the constant function 1. Oops.
Yan.
Bakit? Bakit nyo nasabi na... ano pa? Ito lang ba? Or you want to add something to it?
Sir, shall we include 0?
Pag in-include nyo yung 0, yung constant function 0, remember, ang candidates lang ng basis ay nandun sa vector space, right? Ang vector space natin ay Kernel L. So, ibig sabihin, ang candidates lang para sa basis ay mga constant functions. However, if I put 0 into it, sinabi natin na kapag ka meron kang 0 sa set, automatically linearly dependent na siya. Pero kasi we're talking about basis. So, para maging basis, dapat linearly independent siya. So, ibig sabihin, out of the question yung pagdadagdag sa 0 function. Kasi pag dinagdag ko si 0 function, automatically yung set ko magiging linearly dependent na. Pero basis should be linearly independent. So, hindi pwede. So, so far, ang na-accept pa lang natin na element ng basis ay ay yung constant function 1. Sa itong 1 na to ay f of x equals 1 for any x in 0, 1. So yun yung ibig sabihin nung double struck 1 ko dito. Now, do we need to add another matrix, another element to B? Or is it enough to span kernel L? Kailangan ko ba bang magdagdag? Or kaya bang masulat lahat ng elements ni kernel L as a scalar multiple of 1? Kasi kung hindi ko kaya, kailangan ko magdagdag pa ng elements kay B. Kasi di ba ang usapan, dapat lahat ng elements ng space. In this case, lahat ng element ni kernel L should be written as a linear combination of elements of the basis. But is 1 enough to generate the entirety of kernel L?
Yes, sir.
Yes, that's right, Miss I. Tama. Kailangan ko siyang kaya na ni constant function 1 to generate all elements of the kernel. Bakit? So, halimbawa, ano ba yung laman ng space? Ang laman ng space ay f of x equals c. Now, f of x equals c can be written as c times f, right? Sorry, not c times f, but c times 1. Kung kahit anong constant function, scalar multiple lang siya ng f of x equals 1, right? Kasi halimbawa, meron kang f of x equals 5. Constant function siya. So, nasa kernel siya. Pero yung f of x equals 5, pwede ko siyang isulat na 5 times the 1 function. Alright? So, ibig sabihin, scalar multiple na siya. I can also do that for f of x equals -3, f of x equals -1/2, f of x equals pi to the log of 7, etc. So lahat ay scalar multiple lang ng constant function 1. So that means a basis for the kernel is the set containing the 1 function. All right. So I guess, I think Edward, Jeng, Mamrina, and Miss I. Okay, just remember you get 1 point for joining the discussion. So dagdag na lang dun sa markup later. Ipunin nyo na lang until the last day nyo na lang i-submit yung markup item with a statement kung ilang points ina-gather nyo from the recitation. Okay? Yung pala dapat yung ginawa ko nung simula pa, no? Para hindi lang ako yung nagsasalita. Okay. So with that, we can say that the dimension of the kernel of L is equal to 1. And actually later, we will give a special name for the dimension of the kernel. Perhaps I can spoil that kasi i-end na naman natin yung session in a few. So I'll say this is called the nullity. But it is defined later down in the module. But the dimension of the kernel is called the nullity of your linear transformation. So instead of writing dim ker L, we can write it as null of L, read as the nullity of the linear transformation L, that is the dimension of its kernel. And for our specific example, for the derivative map, the nullity of the nullity of the derivative map is equal to 1, because the dimension of the kernel is equal to 1. But we'll go back to the nullity later, or next time when we talk about the rest of the module. And then let's try to do this. The next thing is to find the range of the linear transformation, and it's a little bit trickier. So the codomain is the set of all continuous functions from 0, 1 to R, right? So when I defined L, sabi ko siya ay from Z1, C1, papunta kay C, right? So ibig sabihin ang codomain ko ay C01. So ang mga candidates para maging elements ng range ay mga elements ng codomain. All right? Now let's try to see that. So, and that's what I meant. That's what I am mentioning there. Yung range ay laging subset ng codomain. Now let's see if I can generate all elements of the codomain as an image of an element of the domain. Okay. So here I'll take an arbitrary element of the codomain and test. Kaya ko ba makahanap ng element ni domain ng LF ay equal kay G, which is an arbitrary member of the codomain. So G is an arbitrary element of the codomain. Makakahanap ba ako ng element ni domain, say F, ng LF ay equal kay G? Okay? But hopefully, maalala nyo yung fundamental theorem of calculus. And that's what I'm going to use here. Essentially, I can define a function f to be this guy. Okay, see, f of x ay equal lang sa integral of g of t dt from 0 to x. Okay. So note that this is well defined because g is continuous. Ang integral ay laging defined for any continuous function, right? And the integral function actually is also continuous. So that means f is a C1 function, because by the fundamental theorem, it will also have a derivative. And then pag kinuha ko yung LF, pag kinuha ko yung image ni F under the linear transformation L, okay? So I'll just replace L by how we define F, which is in terms of G. So, but the image under L is just the derivative of the function inside L. So L of this guy will just be the derivative of this guy. And if you recall the first part of the fundamental theorem of calculus, there's a typo in the handout. Hindi ko alam kung bakit ang daming typos ngayon. Siguro late night ko na to sinusulat. But anyway, the derivative of the integral, of course, G must be continuous. The derivative, the variable to which the differentiation is carried out is the same as the upper bound. The lower bound is a constant. Then the fundamental theorem of calculus tells us that the derivative and the integral operators will sort of just cancel each other out, leaving us with just the integrand evaluated at x. Okay? So here we have shown na merong function f dun sa domain. And that function is this guy, na pag nilagay ko sa loob ni L, ang makukuha ko ay yung preset or predetermined arbitrary member ng codomain. So, ibig sabihin na ang range natin ay set of all C1 functions. Okay? Because set of all continuous functions. Because again, we were able to show that whatever continuous function you give me, I can always define f this way, and that f evaluated or transformed under the linear map L will give me the function g that you gave me earlier, showing that the range is exactly the set of continuous functions. Okay, and then have we? I don't remember if we mentioned somewhere in the previous parts of the module or in the previous modules what could be a canonical basis for the set of continuous functions. Parang wala, no? Wala tayong basis for the set of all continuous functions. Yeah. But I'm telling you that the set of all continuous functions doesn't have a finite basis. So ibig sabihin ang dimension ng set of all continuous functions ay ang basis niya has infinitely many members. So that means that this has infinite dimension. So the range has the range here has an infinite dimension because it is equal to C of 0, 1. But have I proven that the range is always a subspace or hindi pa? Yeah. Parang naging off-topic dito. I should have proven that the range is a subspace earlier. Pero nakalimutan ko siya and I don't want to rewrite the entire thing, so I just introduce it later. So that's why here in this example, I did not talk about the dimension of the range because I'm not sure that the range is a subspace yet, but that will be proven later. But I guess, major takeaway here for today's meeting, we learned what the kernel and the range of a linear transformation is. We saw that the kernel is always a subspace, and so it is a vector space on its own right. So we can calculate, or we can find a kernel, we can compute the dimension of the kernel. But finding the dimension of the kernel might be tricky because you need to find a basis for the kernel. And it might not be easy to find a basis for the kernel. Because again, all we know for a basis is that it should be a linearly independent set and it should span the entire vector space, right? But the problem is, what we are used to is proving that a set is a basis. Pero mahirap na mag-start ka from scratch and think of a basis for the kernel. And that's why it would be important, or it would be advantageous if you can recall yung mga canonical bases na alam na natin from previous examples. So dun usually tayo magre-rely. Unless you have to do your research and find a canonical basis for some subspaces, okay? And then finding the kernel is, I think, is easy because kailangan nyo lang i-compute yung solutions ng LA is equal to the 0 vector. That should be straightforward. But again, the challenge is to find a basis for the kernel. And then finding the range is also tricky. So far in the previous two examples, parang lagi lang ako nag-start with my guess for the range. I always guess that the range is always most likely is the codomain. But at least we have found an example wherein the range is just a subset of the codomain. Pero medyo tricky siya kasi kailangan yung hanapin lahat lang ng posibleng images under the linear transformation. Okay? So, but I suggest we end here para hindi naman information overload. We had been here for how long na? 2.5 hours na. So I don't think it's healthy to go on. Anyway, we are not too much worried or concerned about the time. Gusto ko lang ay yung may mapulot kayong konting bago with this course. Yes, Sir Edelmar.
Sir, I would like to have the answers key in problem homework 3, sir, homework 3. Kaya lang hindi ko ma-download, sir. Although I've done my assignments, I uploaded
Okay.
all ganun lang, sir.
Pero naano niyo po ba, na-access niyo yung webpage, yung link dun sa answer key?
Sir, hindi po ma-download.
Pero na-view?
Sir, yung mga sa web personal mo, sir, nabasa ko yung yung mga sa web personal mo, maganda yung mga nandoon, pero yung answers key, sir, di ko ma-download.
Pero na-view or hindi rin?
Hindi po na-video, sir.
Hindi po, sir, na-video, sir. Ang nabasa ko yung mga personal info about sa inyo, sir, yung mga dissertations mo, yung mga researches.
Okay,
Nabasa
okay.
ko, sir.
Sorry. Ina-double check ko kasi ginagawa ko ay binabago ko yung webpage. So hindi nyo rin nakita yung link nung hold on. Baka pwede kong i-ayusin na now. Tingnan ko ano yung naging problema. So if I go to that link, yeah, sorry. Let me see what the problem is. Okay. Okay. Hold on, guys. Check ko lang. Okay, I don't know, baka mali lang yung nabigay ko na link. Pero if you go here, so kung nasa Teams kayo ngayon, you can go, yeah, you can go here on top, and yung tab na answer keys.
Na binigay mo before.
Yep, and then basahin nyo lang yung acknowledgement, click the link, then you'll be directed to this page, and then homework, answer key to homework 3. There should be a link there for homework 3. Na-reach nyo ba tong part na to?
Yes, sir, na-reach ko na yan, sir, nagawa ko na yan. Pero yung concern dapat sa naka-block siya yung link, kaya hindi siya ma-download siguro.
Okay.
Kasi yung 1 and 2 na download ka na yon, yung 3 na lang kasi naka-block siya, hindi siya blue. Parang
okay.
siguro.
Hindi naka-hyperlink, sir.
Hindi siya naka-hyperlink. But what you can
Pero
do
sir,
for
pwede mo
now,
lang yung i-copy, tapos i-paste
i-copy
sa...
nyo lang, kasi paste nyo lang sa browser. Yeah, i-copy-paste nyo lang yung link na yon. Tapos, yun na. Makikita nyo na siya. So, hindi ko pala siya dapat binobroadcast kasi baka yung iba sa inyo hindi pa tapos. Yeah. Gagawin ko siyang hyperlink later pero hindi ko pala siya na hyperlink. Okay, ano nga ba yung sabi ko? Yeah, just a little some things for the homework. Sige, gawin na lang nating ilan. Okay lang ba na 4 na lang yung i-submit nyo? 4 na lang? Is that okay? 4?
Yes, sir.
Okay, 4
okay,
na
sir,
lang. And then ang deadline ay sa 20 nga ba? 20. That's a Tuesday. And then, sige, I can move it to 21. Kailangan nyo ba ng additional day? Or okay na yung 20?
Sir, pa-move po sana kasi may
Sir, pa-move
homework din kami sa kabilang doon sa isang
Sige, sige.
Oo, sir.
Thank you, sir.
May homework. Sir.
I can go down even to just 3. Pero problema ko sa 3 ay pag in-average ko, pagka dun sa tatlo yung ipapasa, magkamali kayo dun sa isa, malaki na yung magiging effect niya dun sa total percentage. And remember, ang grading natin ay average ng mga average ng mga percent. So I can go down to 3 if you agree to it. Pero the consequence is a mistake in one of the homeworks will have a huge impact on your total percentage for the homework. So yun lang. So what do you want? 3 or 4? Maybe mag-poll tayo. Kasi yung
Sir,
iba,
parang
Okay na yung 4, sir.
Sir, parang na-mention niyo po before na you're willing to like consider, let's say, we submit more than the required. Tapos,
yeah.
you just consider a number of them.
Okay,
evidence.
so ganito na lang. So you submit 4.
Oo nga pala, sir, sabi mo last time, sagutan na lang namin lahat, pero yung total score niya is 20 pa din, or yun.
Something
Or
like
15,
that. Sige.
something like that.
Sige. So, pwede nyo sagutan lahat. The deadline would be on the 21st. The perfect score or the denominator for this homework will be 17.5. Sige, 17.5 na lang. So, if you will be able to answer everything, so good for you. You get 25. Kasi 5 yung original items, no? 25 over 17.5. And then yung mga nagre-recite pa, so you have your bonuses. And then I guess, meron akong mga problems na binigay kanina na posible nyo ring sagutan as extra. So pandagdag din. So para malimutan nyo na yung homework 1 and 2 that I think you are very concerned with. So let's see. Pwede nyo tong idagdag dun sa mga sasagutan. I'll make a post about it probably later or early tomorrow. So I have to do something after the class. Pero some additional problems that you can also do. If medyo nahirapan kayo dun sa mga homework problems, this could be alternative submissions. Na-highlight ko na yata siya kanina. Ano yung sabi ko? Okay, so this is one thing that you can submit. Verify that the linear map in equation 42 or the map in equation 42 is a linear map. So pwede nyo rin itong i-try. Okay? Pakita na itong L na to ay linear map. So sige, let's do it 3 points to. And then I think I also mentioned one. Nalala nyo ba yung isa ko pang hin-highlight?
Yung yung sa square matrix po ata yun.
Yung may symmetric. So tapos na tong example 42.
Taas pa yun, sir.
Taas pa?
Sir, sa taas pa po yun. Na-highlight nyo na pala yung isa.
Let's see. Wala na siya.
Sir, kasi sa proposition 18 tayo nag-umpisa.
Okay. Yeah. Ito yung nalala ko about Theorem 19. So, this could be additional problem. So, worth 3 points. Probably, you can, the problem is to design a linear transformation using Theorem 19. So the thing is, you need to define, you can define any V and W that you like over any field that you like. So pumili kayo ng V, W, at saka F. Pero ang crucial, dapat may alam kayong basis para dun sa pipiliin yung V. Alright? So madali lang naman yun kasi we have seen a lot of examples in the previous module about vector spaces and some of the canonical bases. So you can pick any V as long as you know a basis for it, and then please define a linear map on that vector space using Theorem 19. So all you need to do is to pick a function from B to W. Okay, define a function from the basis to W, and show me what is the induced linear transformation. So pakita nyo lang yung linear transformation explicitly. So para mapakita, ayoko na mag-prove kayo na linear transformation siya talaga. Pero ito yung pwede nyo gawin. Kumuha kayo ng tatlong non-basis elements kasi pakita nyo ano yung function value niya under the linear transformation L. So essentially what I want you to do, what you can do for this extra problem is to construct a linear transformation from a basis. So what you'll do again, choose a V, choose a W, choose a field F, anything that you like, and then just make sure you know a basis for your choice of V, kasi kailangan nyo yung basis. Tapos mag-define kayo ng linear transformation L using Theorem 19. Paano kayo makaka-construct ng linear transformation? Pumili lang kayo ng kahit anong function na defined dun sa basis. So it could be cosine of elements of your basis. It could be sine of elements of your basis. So kailangan nyo lang i-define ano si little f. So pag ganun, alam nyo na yung pag-act ng function f dun sa basis, then yung linear transformation could be defined this way. And then I just want to see how your linear transformation or how the linear transformation you invented using Theorem 19 acts on non-basis elements. So pag na-define mo na si L, pumili ka ng tatlong non-basis elements. Then compute the function value of those non-basis elements. So halimbawa, ang vector V nyo ay F2. Or halimbawa, ang vector space nyo ay Z2 squared. So ang laman nyo lang ay 0, 0, 0, 1, 1, 0, and 1, 1. Alam nyo na yung basis para sa kanya. Tapos mag-define kayo ano yung function value para dun sa basis elements. So pagkatapos nun, pag na-define nyo na yung linear transformation L using equation 46.1, computein nyo lang yung function value under the transformation L ng kahit anong tatlong non-basis elements. So para lang makita ko paano nyo kinonstruct yung linear transformation L using Theorem 19. So again, that's also worth 3 points. And then, kung malala yung isa. Or wala na ba akong binigay na iba? Yun lang. So, let me see. Verify that. Tanda ko may isa pa akong hin-highlight eh. Hindi ko lang matandaan exactly where. Yeah. So sige, yun na muna yung dalawang extra problems. So if I remember the last one, then I'll also include it in the thing that I will upload later tonight or early tomorrow. Okay? So yun na yung deal natin. Deadline would be moved on the 21st. You can answer as many problems as you like. There are 5 assigned problems already. You can also choose from the extra problems that we just created. So far we have 2. So I'll put that into writing later. But again, you only need to submit, there's no number of required submissions, but the perfect score for this homework would be 17.5. But that won't be the maximum. So the maximum so far stands at 31. So at most you can get 31 over 17.5. So yeah, I guess that will help you move on from your homework 1 and homework 2 scores. Okay, yeah. Any other concerns? Let's continue this on Monday. So and finish homework and finish module 3. By then, I will upload module 4 na, which would be about a short course on matrix algebra or probably matrix analysis if you want, but it would be more numerical in nature. Okay?
Sir, thank you so much po sa
Sir?
Alright,
consideration.
you're welcome.
Thank you, sir.
Sir, may tanong ako dito sa sa continuous function po.
Aha.
Kasi 'di ba close interval to siya, sir?
Yep.
Kung open interval po ba 'yan? Continuous function pa din ba 'yan?
I think so, yes. Pero yung pakabila ay hindi tayo sure.
Oo, kasi 'di ba pag kung open interval siya, yung 0 at saka 1 hindi kasali sa
Yep.
sa elements in a
Yeah.
sense. So wala siyang unity or additive identity.
Meron pa din kasi yung mga functions naman yung nanggagaling sa C01. Pero yung unity nanggagaling siya dun sa field. Ang field
Okay.
natin laging R. So,
Okay.
actually yung set ay hindi crucial kung saan natin dinidefine yung mga functions. So I think it could be C closed interval 01. It could be C open interval 01. I think it could also be a union of open or closed intervals. That's fine. Pero hindi siya ganun ka-crucial.
Okay, sige. Okay.
All right. So, yeah. So, okay, that's it for now. So, thank you for coming today. Enjoy your weekend. So, magpahinga. Huwag kalimutang magpahinga. So, but I know patapos na yung SEM, so probably nagpa-pile up na yung mga requirements with your other class. So, yeah, but let's see each other again on Monday if you have some questions or for us to finish module 3 and then address your questions about homework 4. And then, yeah, so bye guys. Have a good weekend.
Bye,
Thank
sir.
you po, sir.
Hi, sir. Thank you.
Yep.
Salamat, sir.
By the way, yung
Bye,
mga hindi
sir.
pa nagsasagot ng evaluation, kindly answer the evaluation para rin may feedback on how I handle the course. All right.